Hello everyone, I'm Paul and today we're solving problem 2311, longest binary subsequence less than or equal to k. This is medium and this might seem complex at first, but there's one simple trick that we can use here. So next we will go with intuition, approach and efficient solution. We are given a binary string s and a positive integer k. And our job is to return the longest subsequence of s that makes up a binary number less than or equal to k. So let's say we have this string. We can remove any or none of these elements, and this is how we get a subsequence. So let's say we remove this. A is still a subsequence from this. If we remove this a, this is also a subsequence. If we remove this and this is also a subsequence. And if we don't remove anything, this is also a subsequence. So let's say we're given this binary string and k is 5. Down here we have the constraints, and maybe you're thinking about brute force this, and this is how you can get every possible subsequence. And from this you can check which subsequences are smaller or equal to k and keep the longest and return that subsequence. That won't work because s can be up to 1000, and that will require time complexity of roughly 2 to the power of 1000, and this is a very big number. So we need to think about something more efficient here. There are different possible results in this case. One, for example, is 0, 0, 0, 1, 0. Another one is 0, 0, 1, 0, 0. Another one is 0, 0, 1, 0, 1. So this is valid, and this is also valid. So the result in this case is obviously 5, which is the length of any of these numbers. But the thing here is that we are looking for some pattern that we can use to get always the longest subsequence. Because this is valid, but we are trying to get a pattern here. And we'll look at this result. The pattern will be the following. First, instead of looking for the numbers that we should take from here, we will try to take them all, and we will only remove the numbers that we can't take. So this will be like this. We will transform this into the corresponding binary representation. So this 5 in base 10 is 101 in base 2 in binary. Okay, so this is the binary representation of this. In case you know, in this position we have 2 to the power of 0, this position is 2 to the power of 1, this position is 2 to the power of 2. So if we do 2 to the power of 2 times 1, this is 4, and if we do 2 to the power of 0 times 1, this is 1, and 4 plus 1 is 5, which is this 5 here. So now let's say we position this number here. Now we already see some information here. If we position the binary number for k here, every one that's after the last position should not be included. So we should avoid this, we should avoid this. That's one thing we know. So we should avoid ones after the last bit of k. Another thing we know is that we can't take every 0 after the last bit of k, because this won't have any negative impact, and in fact we can take every 0 in the entire string because the number for all zeros is 0, and this will always be smaller than k. So as a minimum, the longest subsequence will include all zeros. So in this case, as a minimum, we need to return 4. So the second observation is that we can take all zeros. And now the final question is, can we take everyone in this substring or not? And more specifically, can we take this one here or not? Well, here we need to check if this substring is smaller or equal to k, meaning if this is smaller or equal to this, we can take every one here. So in this case, this substring in base 10 is 2, and 2 is smaller than 5. This means that we can take this one. So for the final result, we are taking 1, 2, 3, 4, 5 characters. So the result is 5. Now let's say we have this string and k is 5. The binary representation of k is this. And now we will do the same as before. We will draw a line here and we will focus on these elements first. So we know that we can take every 0, and we know that we can't take none of these ones because they come after the last position of the binary representation of k. And now the final question is, can we take this or not? So we know that 1 is smaller than 5, so we can take this. Now if we take this and this, the base 10 representation of this is 3, and 3 is also smaller than 5, so we can take this also, meaning we can take these 2. Now let's say we are trying to take these 3. The base 10 representation of these 3 is 4 plus 2 plus 1, 7. And 7 is greater than 5, meaning we can't take this one in this case. So for the result in this case, we can take 1, 2, 3, 4 elements. So we return 4. And now maybe you're wondering, why do we put the binary representation of k, meaning this, here in the rightmost position? Why don't we compare these 3 bits against these 3 bits, for example, or against these 3 bits? And the answer is, we put this here because here it has the lowest impact in this binary string. Let's say we put k here and we compare these two. Well, in this case, we would need to remove every one that's before this, because this is the greatest possible number that we need to achieve. And we also would need to remove this one because this comes after the last bit. And the base 10 representation of this is 1, which is more than 5. So we could take this, this, and this, but this won't be the longest subsequence. Given that we are trying to find the longest subsequence, we need to compare k against the lowest impact bits, meaning we need to put the binary representation of k here. So finally, let's see how are we solving this. We'll iterate this from right to left in this direction. So the I pointer is here initially, and we'll check if this is a 0, we add that in the result. If this is a 1, we will check this against k. 1 is more than 5, so in this case we add this to the result. So in this case the result is 1, and we will keep track of the ones that we are adding. So we'll have another variable, we'll call this current, and up to this moment we only have a 1 here, so we put 1. Now we have another 1, so we are checking if current plus another 1, meaning this is smaller or equal to k, and the base 10 for this is 3, and 3 is smaller than 5, so we can add this one to the result. So now the result is 2, and this is current. Now we have another one, and we are still in bounds for the amount of bits for k, so the new current is this, meaning 1, 1, 1. So we are checking if this is smaller than k, and the base 10 representation for this is 7, which is greater than 5, so we can't add this. Now we continue, we have another one, but now we are out of bounds here, meaning we have more bits than the binary representation for k, so we can't add this to the result. Next we have a 0, so we add 1 to the result. This is 3. Here we have another 0, so the result is now 4. Finally we have another one that's out of bounds, so we can't add this. And here we end the loop and we return 4. Time complexity for this is big O of n for the size of the string plus log k. And this log k is the required complexity to get the amount of bits, in this case 3, for the given k. And space complexity will be big O of 1. So now let's go with the code and hopefully you will get the idea. First we need to get the amount of bits in k. And there are two ways to do this. You can use a Python function which is bit underscore length. So this returns the amount of bits in k. But I want to show you how to do this manually also. For this the bits are initially 0. Now we will copy k. We'll store this into a variable. We'll call this num. So this equals to k. And now while we have something, well, we have a number, num divided equal 2. We are using 2 because this is binary, and bits plus equal 1. So you can choose whatever you want here. Both of these methods work. Now the result is initially 0 and we need to return this result. Current is also 0 initially, and now we will reverse s. We are doing this for convenience to make the code more readable. And now we will enumerate this, and each time we'll get an index and a character. And now in this loop, if the character equals to 0, we add to the result a 1, else, meaning if the character is a 1, we add to current 1 left shift I. And now if I is smaller than the amount of bits we have and current is smaller or equal to k, we add 1 to the result, and finally we return the result. So if the character is 1 and the current index is in bounds, meaning it's smaller than the amount of bits, and our current binary number, which has all 1s, is smaller or equal to k, we add 1 to the result. And finally we return this. So now let's submit this and see if it works. As you can see, this works and it's very efficient. Now here is another code that I wanted to show you. Maybe you find this more intuitive. So we do the same here. We take the amount of bits. Result and current are initially 0, same as before. We run the same for loop. And now we're checking if the current index is smaller than the amount of bits in k. We update current with whatever we get in the current character. This might be a 1 or a 0. So this is how we keep track of current. And if current is smaller or equal to k, we just add 1 to the result. And if we exceed our bounds, meaning if I is greater or equal to bits, and if the current character is a 0, we can add 1 to the result. And finally we return the result. So maybe this is a little bit more intuitive for you. So I will submit this just to show you this works. As you can see, this also works and might be easier to understand. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.